Okay, welcome back. Our next speaker is Josephine Sung from KAIST, and she'll tell about entropy in quantum gravity. Let's welcome.
So I'd like to start by thanking the organizers for this opportunity to talk about my work with my collaborators done about 10 years ago. So while preparing this talk, it was a good opportunity for me to review some of my own work and also some related work. So I'll try to give a somewhat broad overview of connections between entropy and areas in quantum gravity, but also, of course, I'll review in some depth the work we got our FSA for as well. So the earliest known connection between entropy and area goes back to the Bekenstein formula in 1972. And famously, it says that the entropy of a black hole is given by the area of the horizon in units of 4G Newton. Okay, and the motivation for this formula came from thinking about putting stuff into a black hole. You know, the mass of the black hole increases, then its area increases. And with this identification of area with entropy, it seemed at that time that one could formulate a generalized version of the second law of thermodynamics. Okay, so the sum of the entropy of the black hole and of the stuff outside the black hole is always increasing in time. Okay? And in fact, a general proof of this was completed about 10 years ago by Wall. And the crux of the argument in the proof for this generalized second law actually follows from Einstein's equations. So Einstein's equations constrain the evolution of areas, and it leads to this second law. Okay, so I'd like to bring your attention to the fact that the horizon was identified with a particular kind of entropy, which is thermodynamic entropy, right? And thermodynamic entropy captures what we don't know about a system, okay? And mainly it's defined by the fact that it's governed by the four laws of thermodynamics. So for a black hole, in addition to identifying entropy, as in the previous slide, we know that it has a temperature given by kappa, surface gravity of the black hole over 2 pi. And with this identification of the temperature, as well as the entropy, one can show that a black hole satisfies laws of black hole mechanics, which are analogous to all four laws of thermodynamics. So for example, the first law says that the change in mass of the black hole is given by the change in area plus a term involving angular momentum, which is analogous to work in thermodynamics. So this term is entropy, this term is work, and this term is energy. Okay, and example, the zeroth law of mechanics says that for a stationary black hole, which corresponds to equilibrium, thermal equilibrium, the surface gravity or the temperature is constant over the event horizon. Now, much more recently, still about 20 years ago, in the context of holographic duality, a connection was discovered between von Neumann entropy, a different kind of entropy, of quantum degrees of freedom and extremal areas in gravity. So this is the Ryu-Takayanagi formula, and it says that the von Neumann entropy of a density matrix of some region in the boundary theory is given by the area of a surface that is anchored on the boundary of that region and which has extremal area. So does everyone know about the holographic duality? I can assume that. Okay, so it's a duality between quantum systems and a gravitational theory in one higher dimension. Okay, so unlike the Bekenstein formula, the Ryu-Takayanagi formula involves a fine-grained entropy, because the von Neumann entropy is determined completely by the quantum state, the density matrix rho, and it is independent of any observer's knowledge of the system. Okay, so for example, for a stationary black hole, again in holography, the RT surface, the surface according to the prescription on the previous slide of finding the surface with extremal area, it coincides with the horizon of the black hole. And this is consistent with the fact that for a thermal state on the boundary in this duality setup, for a thermal state, the thermodynamic entropy of the state equals the von Neumann entropy. Okay, but in general, right, if you have a time-evolving black hole, for instance, the horizon and the RT surface are distinct. They have no reason to coincide with each other. And so a famous example is an evaporating black hole, where if one calculates the correct RT surface, it approaches the event horizon from the inside. So in this picture, the area of codimension 2 surfaces is going to decrease inside the horizon, away from the horizon. The fact that the RT surface is inside is going to imply that the von Neumann entropy of the black hole system is always going to be smaller than its thermodynamic entropy, which makes sense. Okay? And in particular, it approaches the horizon in such a way as to reproduce the Page curve, which is the curve for how the von Neumann entropy of a black hole should behave, given that we have a unitary system. So the Ryu-Takayanagi formula is a very precise relation in quantum gravity, which we expect to hold quite generally, okay, even in de Sitter space, even in flat space, even in cases where we don't have ADS-CFT, for instance. So for the next few slides, I'll review a derivation of the Ryu-Takayanagi formula starting from holographic duality. Okay. So one can start with the basic premise of holographic duality, which is that there is an equality of partition functions. Okay. The partition function of a quantum system is equal to the partition function of a gravitational system, where the quantum theory lives on some boundary of the gravitational space-time. And we are being vague about, it doesn't have to be the asymptotic boundary. As in anti-de Sitter space, we can just generally assume that there is some boundary in the space-time. We put the quantum theory that describes the degrees of freedom in the gravitational theory. So this is a picture that of the quantum theory on this circle, on this Euclidean time circle, and the gravity theory in Euclidean signature. And so we can derive the RT formula just starting from this equality of partition functions. And the essential ingredient in the derivation, again, comes down to Einstein's equations. Just like we could derive the second law of thermodynamics for the area of a black hole horizon. Okay, the technical ingredient, the technically important ingredient is actually the replica trick in this derivation. So using the replica trick, one can express the von Neumann entropy of some density matrix rho in terms of partition functions Zn. So these are, if you like, n-fold partition functions. So you take the nth power, where n is an integer. So you take the nth power and you take the trace, and this is well defined. But the replica trick is that you analytically continue that result in n, and in this case to n to 1, and you assume that you get a reasonable answer. But as a result of using the replica trick, we can express the von Neumann entropy of a density matrix in terms of these Zns. And via holographic duality, these Zns are given by gravitational path intervals. Because remember, we had an equality between partition functions, where the gravitational path interval should satisfy periodic boundary conditions. So n equals 1 is the actual quantum system. So you go around the Euclidean time circle once. for n a larger integer, you have to go around a larger Euclidean time circle. And so you just enforce n-fold periodic boundary conditions. And if we work in the semi-classical limit, these n-fold partition functions are given by e to the minus action of the gravitational solution. Any questions? Please feel free to interrupt with questions. Okay. So how do we derive the Ryu-Takayanagi formula? Well, the entropy, if we go back to this replica trick, we can express the entropy in terms of actually solutions that have a conical deficit at the origin. Okay. So what we did here was we started out with the solution for Zn, and it has a boundary circle with periodicity 2 pi times n. And we think of dividing it by n. Okay, so we think of 1 over n times the action of the solution. And this is actually equal to a gravitational solution with a Euclidean time circle that is just 2 pi at the boundary, but with a conical deficit inserted at the origin. A subtlety is that you have to subtract the singularity that comes from the origin, but the bulk, the contribution to the partition function from away from the origin should be equal to this 1 over n times the contribution from this larger solution. So the advantage of thinking about 1 over n times Zn in this way is that we can write the von Neumann entropy as a derivative with respect to n of this solution with a conical singularity of the origin. And because we are perturbing about the n equals 1 solution, this derivative or variation vanishes everywhere except at the origin. So if there is some contribution, it's going to come from around the origin. And if we think about where the origin, meaning where the Euclidean time circle vanishes in the bulk, it's actually constrained by Einstein's equations to be where the codimension 2 surface has minimal area. So this is where Einstein's equations come in. So to complete the derivation of the Ryu-Takayanagi formula, you have to calculate this variation explicitly on this geometry. And it is a contribution coming from, again, the surface, the point at which the codimension 2 surface has minimal area. And the actual form of the contribution is the area of that surface. Okay? So in fact, the variation of the action of the conical geometry is an area term localized at the minimal surface. So far we've been talking about just some arbitrary density matrix, right? And having some dual gravitational geometries. But the RT formula deals with spatial regions, if you recall, with spatial regions in the boundary theory in holography. So we have to connect what we just said to the replica trick that we perform to calculate the von Neumann entropy of spatial regions. Okay? So this was work that is reviewed quite elegantly in this paper, actually. But you can think of, again, we work in Euclidean signature. You can think of a path integral over a geometry where you join. So this is the interval for which you're calculating the entanglement entropy, and you join n copies of your theory. And these give you the Zn's appearing in the replica trick. So we can apply what we just said to this replica geometry, and the Euclidean time coordinate, if we think about where the Euclidean time coordinate is, it goes around in the plane that's formed by Euclidean time in the theory and a direction perpendicular to the boundary of your spatial region. Okay, so that was very nice because we had this mysterious RT formula connecting von Neumann entropy to extremal areas in gravity, and now it seems we just reviewed an argument that shows we can derive the RT formula starting from holographic duality. But a limitation of this argument that we reviewed is that it only works in Euclidean signature, right? And we have to use the replica trick. So this applies, we can analytically continue Euclidean signature mostly when we have a time-independent quantum state. Okay, so there are some exceptions where you have time reflection symmetry and you can still continue, but mostly this means working in Euclidean signature means we have a time-independent state. But the RT formula is actually robust and applies in its most general form even when we have a time-evolving quantum state. Okay, so the original RT formula involves minimal surfaces, and it works only in time-independent states. If you slightly generalize the formula, which was done by these people, it applies even for time-evolving quantum states. So this suggests, and I think this is a very important point, that there is a way to understand the RT formula in a way that is intrinsic to gravitational dynamics in real time. So even though we have this very nice technical trick, we have to try to not use it and try to understand the RT formula in a different way. Okay, and another point is that we assumed a holographic duality, right? We assumed that there was an equality between a quantum theory and a gravity theory and inferred the RT formula. But one question you could ask is, can you go the other way? So can you use the RT formula to learn more about how holography works? Because we don't know everything about how holography works. There are many questions that we'd like to answer, and maybe we can go the other way and try to say something about how holography works, starting from the RT formula. So this question was actually the impetus leading to our FSA work. And so next I'll start by discussing something called modular Hamiltonians. So the modular Hamiltonian is a von Neumann entropy-related object in quantum information theory. It's just given by minus the logarithm of the density matrix. So this is called the modular Hamiltonian operator. So this is a picture of the modular Hamiltonian, the action of the modular Hamiltonian for half space. And it actually just coincides with Rindler time, so boosts. But as I'll mention later, this is a very special case, or this is one of a class of cases in which the modular Hamiltonian is local. In general, the modular Hamiltonian, you could imagine for an arbitrary region in some QFT, you cannot expect that it can be written as some space-time integral of local operators, right? Because there's some complexity of calculating the von Neumann entropy, and the modular Hamiltonian operator should have some corresponding complexity here. Okay, but what can we say? Okay, we know that it's some very complicated non-local operator in general, but what can we say about modular Hamiltonians in relativistic QFT? So the of some QFT region R should be associated with a region called the causal completion of R. Okay, so the causal completion of R is the space-time region in which the quantum state is entirely determined by the data on R. Right, so you can see this is the region of the plane where you subtract the parts that are influenced or in causal contact with the complement of R. Also, it's a Hermitian operator because it's the logarithm of a positive operator, the density matrix, possibly unbounded, okay? And it acts on the Hilbert space of states in this, in this causal completion, so right. You can think of it as acting on the algebra of states corresponding to this causal completion. And conjugation by the modular Hamiltonian, which is called the modular flow, is an automorphism on the algebra of bounded operators in CR. Okay. So when is the modular Hamiltonian local? So generically, it's non-local, but when there is a U1 symmetry, when there is some U1 symmetry generated by a killing vector or a conformal killing vector, the modular Hamiltonian is an integral of the energy momentum tensor along some spatial slice of your causal completion. Okay, so one example, of course, half space in the vacuum of any QFT is an example where we have U1 symmetry. Another example is when the boundary of your region is a sphere in Minkowski space and your state is the vacuum of a CFT. Okay, so what's special about this case is that you can map the causal completion of this region bounded by a sphere to some hyperbolic space and the vacuum state to a thermal state, and then it's actually mapped to a black hole geometry. So using this kind of argument, you can show the Ryuta-Yanagi formula, of course, in this limited case, by just using the Bekenstein formula for a black hole. And notice that you don't have to rely on Euclidean geometries. But this was a successful attempt by these authors to show the Ryuta-Yanagi formula without relying on the replica trig. Yeah, but of course, it works only in a limited case. Now, for a general modular Hamiltonian in a QFT, it will reduce to this form if you are very close to the entangling surface, right, as compared to any other scales in your problem. So this gives us some intuition about the UV divergences in an arbitrary modular Hamiltonian. No, just some sort of translational symmetry. Okay, so the question that we asked was, in the setting of holographic duality, can we map this modular Hamiltonian of a boundary region to some well-defined object in the bulk gravity theory? Because in general, it's very hard to get a handle on in quantum field theory, but maybe in the setting of holographic duality, we can say something about it that's useful. And the answer was yes, as we answered in these papers. So we start with the RT formula, improved to order G Newton to the 0. So the extremal area term in the RT formula gives you the leading piece in the von Neumann entropy and an expansion in small G Newton. To get the next order term, you have to include the von Neumann entropy of quantum fields in your bulk theory on a spatial slice outside your surface. So you have some codimension 2 surface, and you have to include the von Neumann entropy in this region on some outer region relative to the surface in order to get the next order term. And you also have to include some counter terms, but they're localized on the surface. Okay. So given the form of this full Ryuta-Yanagi formula, one can infer that if we are considering some reference state sigma, okay, so imagine some reference state sigma that is described by a bulk gravity solution. What is its modular Hamiltonian? It has some nice, we have some nice simple bulk expression for what the modular Hamiltonian of the boundary state is. And it's given by an area operator plus the modular Hamiltonian in the exterior region, plus another term that gives you the counter terms in the previous RT formula. And this expression only applies, it describes the action of the modular Hamiltonian on nearby states. And by nearby, I mean states rho that are related to sigma by bulk perturbation theory. Right? So we imagine exciting, putting in a few more particles in the bulk, and they don't react by too much. And then we can say that this expression holds. So let's have a closer look at the operators on the right-hand side. Okay, so these are all operators that are defined in the bulk theory viewed as an ordinary quantum field theory. So we are assuming the holographic duality holds with an ordinary quantum field theory in the bulk. area operator is going to be the integral of a metric perturbation, of metric perturbations over the extremal surface. And notice that the extremal surface is invariant under small changes because it's extremal. So it's a gauge invariant quantity here, okay? Imagine just quantizing your theory, which includes the metric, viewed as an effective field theory, so just in semi-classical quantization. Okay, so it's the metric perturbation operator H with a hat. The second term, K bulk, is the modular Hamiltonian of this outer region, sigma R. So in this picture, we have this boundary region R. Then we have some spatial region that extends from R to the extremal surface S. And it doesn't matter, there is an arbitrariness here. You can choose any spatial slice that goes from R to S. But the point is that it doesn't matter because they all define the same causal completion in the bulk. Okay? Just think of some spatial surface that extends from R to S. And because we have an ordinary quantum field theory in the bulk, we can think about the modular Hamiltonian of the quantum state in the bulk theory corresponding to that region. So this bulk modular Hamiltonian produces this von Neumann entropy here in the RT formula. Then we have some operator that is again localized on the extremal surface, just like the area operator, and it leads to counter terms in the previous expression here. But you'll see that this operator really doesn't matter because it factors out of a lot of quantities because it's localized on the extremal surface. Yeah. Well, the graviton contributes, but in a lot of quantities that we consider, like the relative entropy, fortunately, their contribution will not be important. So maybe a better explanation is think about a gauge theory. So the closest thing is if you think about a gauge theory, there is an ambiguity in how to define the von Neumann entropy in a gauge theory, depending on what boundary conditions you put in the region that you're looking at. And your definition of von Neumann entropy will depend on those boundary conditions. But if you compute relative entropy between two states, that ambiguity goes away. And a similar story holds for the contribution of gravitons. So there is, we basically expect to sum over boundary conditions, but we expect that that contribution goes away when we compute things like the relative entropy. Oh, it's been. Okay, so now I'll explain perhaps the main result in our paper, which was that relative entropy on the boundary equals relative entropy in the bulk. Okay, so what is relative entropy? The relative entropy of a quantum state rho with respect to sigma is given by the following formula. So trace rho log rho minus rho log sigma, and it's a measure of distinguishability between the two states, and it has some nice properties. It's very controlled and clean to calculate. So first of all, it's positive, it's always non-negative, and it is monotonically decreasing under coarse graining. So imagine applying a completely positive map to these states rho and sigma. The relative entropy between those two states after application of the mapping will be smaller than the relative entropy between the original states. Okay, that means the states have become less distinguishable after coarse graining. And as I was just saying before, even when the von Neumann entropy of regions is ambiguous, relative entropy is well defined. Okay? So for example, suppose the von Neumann entropy changes by the expectation value of some local operator. Okay? As long as this local operator is the same for the two states for which we're calculating the entropy, the relative entropy is preserved because the contributions cancel between these two terms in the logarithm of the states. Now consider our previous expression for the modular Hamiltonian of some boundary region. Okay. If we have two states rho and sigma, which are related by bulk perturbation theory, the area term here, the area operator and the counter term operator should be identical in the formula for their respective modular Hamiltonians. And that means, similarly to what happened in the previous slide, they cancel in the definition of relative entropy. So as a result, only the bulk modular Hamiltonian matters. And we have the equation that the boundary relative entropy between these two states is equal to the relative entropy in the bulk quantum field theory of the bulk states that are dual to the boundary states. So this was our main result. So the upshot, starting from the Ruta-Kanagi formula, okay, we have learned that the holographic mapping or holographic duality preserves relative entropy. So we managed to learn something about holography starting from RT. So some implications of relative entropy equals relative entropy. One sort of consequence is that we can learn about subregion duality in holography. So if we ask the question, what region in the gravity dual is in correspondence or dual to the boundary region R? Naively, you might think about a region called the causal wedge in the bulk. So the causal wedge is the intersection of the future and past of this boundary domain in the bulk quantum field theory, and it's this red diamond. And naively, this could be a candidate for the bulk region that's dual to region R. But our results about the modular Hamiltonian and relative entropy imply that the appropriate bulk region that is dual to R is actually the entanglement wedge. And the entanglement wedge is the causal completion in the bulk of this surface that extended from R to all the way to the extremal surface. So in general, this entanglement wedge is larger than the causal wedge. So we have that this entire entanglement wedge is described by the data on R. One can make this a little more specific. So we can ask this question, given some local field operator in the bulk QFT, how can we express it as a smearing of operators in the boundary? So this is the problem of bulk reconstruction in holography. And in cases with the Yuan symmetry, where the boundary module is local, we can find using equations of motion in the bulk that we can express a local operator in the causal wedge of the boundary region as an integral over this boundary region CR, over the causal development of R in the boundary. Okay, so in addition to coordinates over R here, I have this coordinate tau, which corresponds to translations generated by the local modular Hamiltonian. And the kernel G follows from bulk equations of motion. Now, in the case with Yuan symmetry, it also happens that the causal wedge coincides with the entanglement wedge. So this result actually tells you that you can reconstruct an operator in the entanglement wedge using as a smearing of boundary operators in the causal development of R. Now, in our paper, we made the natural conjecture that even in cases where the boundary modular Hamiltonian is non-local, even in cases without Yuan symmetry, we can reconstruct an operator in the entanglement wedge in this form. So this is basically the same formula as before, but now the S parameterizes modular flow, where the generator does not have to be local. So it's a flow in the abstract space. It's a flow in an abstract sense. It is not local but it's generated by the non-local modular Hamiltonian. And this G is some kernel, and we can say we can actually obtain this kernel concretely, at least in principle, if we think about the following. So by bulk causality and the expression for the modular Hamiltonian that we had before, these terms that are localized on the extremal surface, the area operator and the counter term operator, they commute with an operator inside in the interior of the entanglement wedge, right? So if you're in the interior of this blue region, then operators localized on the extremal surface should not affect it by causality, okay? Because light rays from this extremal surface define the boundary of the region. So we have the implication that the action of the boundary modular Hamiltonian, which is involved in this expression, evolution in modular time S, is equal to the action of the bulk modular Hamiltonian. And in the bulk, our fields are free to lowest order in G Newton. So this expansion here, we can actually understand as an expansion in the algebra of the bulk entanglement wedge. And it's because we can often calculate the modular Hamiltonian corresponding to free fields, we can in principle get some concrete expression for this kernel. Okay, so I'll finish with some discussion. So some open questions that remain unanswered and which have surfaced recently in the literature. From the point of view of a quantum theory describing gravity, what is happening as an observer falls into the interior of space-time, right? How do we describe its experience, right? We still haven't answered this question. Although we know about the Ryutake-Yanagi formula and the modular Hamiltonian and so on, we still haven't answered this question of what is happening in, say, the SYK model as an excitation falls into the space-time. And relatedly, what is space-time made of? Okay, so this question is actually related to, if you think about it, how you can interpret surfaces that are non-extremal. Because as this excitation falls into this two-dimensional space-time, it's passing through areas that are non-extremal. So how do we interpret or identify the areas of those non-extremal surfaces in the boundary theory? Okay, and to answer these questions, I think it is helpful. I believe it's helpful to go back to the Bekenstein formula, okay, to go back to results that came before the Ryutake-Yanagi formula, which related, areas to thermodynamic entropy. Okay, so since the Bekenstein formula, results have actually accumulated showing that arbitrary areas obey thermodynamic inequalities. So it doesn't have to be the area of the black hole horizon. You can choose an arbitrary area and it obeys various inequalities that are thermodynamic in their appearance. So one important example is the covariant entropy bound. Okay, so the covariant entropy bound says that the change in area of surfaces, okay, so imagine some congruence of null geodesics, and think about the area at the top and the area at the bottom. The change in area bounding a non-expanding null hypersurface has to be greater than the entropy carried by matter passing through that null hypersurface. Yes, so we are thinking about specifically a non-expanding null hypersurface. Oh, yeah, so sorry. The next result is going to involve arbitrary areas, and the next result subsumes this covariant entropy bound. Okay, so this was the original entropy bound by Busseau in 1999. Now, the quantum focusing conjecture, which is a slightly more recent result, it subsumes a quantum version of this Busseau bound and also a generalized second law for causal horizons. So the generalized second law that I mentioned in connection with black holes actually applies for causal horizons in general. And we have a statement that involves arbitrary areas now that imply these thermodynamic statements. So what is the quantum focusing conjecture? Okay, we define a generalized entropy for an arbitrary Cauchy splitting surface sigma. Okay, Cauchy splitting surface means that you have a Cauchy surface, right? A surface that determines the evolution of your entire system, and it splits it into two. And then you can assign, the proposal is to assign a generalized entropy to such an arbitrary splitting surface that is given by its area plus the von Neumann entropy of some outer slice. And this outer slice, you can either choose to be this slice or this slice, it doesn't matter. And then you have counter terms. Now, the next step is erect an orthogonal null hypersurface emanating from sigma. And you consider the response of this generalized entropy to deformations of sigma along this null hypersurface. So this is a picture of a congruence of null geodesics along this direction. And if you define, okay, so this is called the quantum expansion. You're looking at the rate of change of this generalized entropy divided by the area, the original area. The statement of the quantum focusing conjecture is that this quantum expansion is negative. And it turns out that this inequality implies the previous, for example, the previous generalized second law and a quantum version of this Busseau bound. So I think these results are suggestive, okay? So areas in general seem to have some thermodynamic character. Okay? So as a challenge / not yet complete proposal, I want to argue that given the evidence that areas in general represent a kind of thermodynamic entropy, and the fact that you can interpret von Neumann entropy as a special limit of thermodynamic entropy, right? So von Neumann entropy, if you remember, is completely determined by the quantum state. So if you like, it's thermodynamic entropy in the limit of complete knowledge about your system. So given these two things, it seems reasonable to posit the following. We need to arrive at a precise notion of thermodynamic entropy that takes into account the information carried by an observer. And the proposal is that this is what areas in space-time are made of. If you look at this picture, as the excitation falls into the space-time, the information that this excitation has about its path, well, I won't say more, but it changes, and that's why the area changes. And finally, when you get to the Ryutakyanagi surface, that's when you have complete information about the system. And so if one could formulate a precise notion of such a thermodynamic entropy, we would have some answers to these questions. Okay, I'll end here. Thank you for your attention.
And for questions?
The general question, in your talk, you assume you had some semi-classical space-time and you look at the quantum fluctuations around it. Is it clear what is the notion if you are in a deep quantum regime where there's no semi-classical space-time?
Yeah, so all these results are in the semi-classical regime. So I would say, as long as you work in the semi-classical regime, you can expand in small g Newton. But
Is there a definition away from the semi-classical?
Sorry?
Maybe not calculable, but is there a definition what happens away from the semi-classical?
Well, I mean, one thing I can think of is in string theory, people have computed, the microstates of a black hole. So that's that's one example, and it coincides with the Bekenstein-Hawking entropy, right? The area. Wait, is that also? Well, yeah, I would say that in general we deal with the semi-classical regime, and we don't really think about the the quantum regime that much. Yeah.
There's no definition pattern.
Yeah, yeah.
I have a question about your mention about the quantum expansion. So maybe in my opinion that we need to define operator of expansion. So that means it's quantum. So but that in your definition so this expansion is just not an operator. So do you think that we need to define this kind of operator of expansion? Then it will operate on a state. Then we get the values of the expansion. Then to define a quantum horizon. So that's a question.
So you're saying this operator. Sorry, what? Expansion? Quantum expansion. Okay, yeah. Yeah, maybe you can think about doing that. Yeah. Mm-hmm. Yeah. Well, first of all, I see one problem, one immediate problem, which is that we are now talking about general areas that are not extremal. So how do you define that in a coordinate invariant way? In the case of an extremal surface, it was invariant under change of coordinates because the surface is extremal. So I see some problems, but yeah.
More questions? Yeah.
If you don't have the Killing vector, what can you say about this non-local modular Hamiltonian? Can you say anything?
Yeah, we can say the various things that I mentioned, the general properties. Yeah. Remember that we had some general properties of a modular Hamiltonian, that it acts on the algebra associated with this causal diamond. And it's...
So you think you can write it out in principle in terms of the boundary information? I mean the bulk.
Yeah, it's log of the density matrix. So if you know the density matrix, certainly you can write it. But in general,
So
if you know the Hilbert space of your quantum system and you know the density matrix of your region, then it's just the log of that density matrix. But of course, in general, we don't have direct access or eclipsed form for those things.
Thank you.
Thank you for the lecture. It seems you are proposing that in general area can be some measure of like entropy or information, but given that the observer has some like partial information. So we know for the minimal surface, naturally the area of minimal surface satisfies some information theoretical inequalities such as the subadditivity. So do you see like area in general, like how can we see like it's a information theoretical quantity or
yeah, to answer that kind of question, we'd have to first make this proposal very precise, right?
Okay.
Match a very precise definition of this entropy. We haven't done yet.
I see. Thank you.
I want to ask how to understand for some quantum mode involved in the entropy calculation, since we know that sometimes we can summing up some quantum correction, maybe from the Schwarzschild or JT sector in some black hole in the partition function. But in the sense of the bulk perturbation theory, sometimes the some mode of like Schwarzschild mode is can only appear in the near horizon region. For the observers at the faraway boundary, it seems he cannot see anything. So how to, in this case, how could we understand in the perturbation theory side, how to understand the entropy definition for the boundary observer?
Yeah, you have to think about the dilaton solution in JT gravity,
Yes,
right? So the dilaton captures this area in JT gravity.
yes, but it's only in the near horizon region, some black hole solution.
Yes, it's in the near horizon region, yes. Yes, so you have to think about, I suppose, the observer as being on a boundary that
Yes.
is close to the near horizon region, but it can still fall closer to the horizon, right? Yeah.
So the observer cannot be very far from the near horizon region. Otherwise, he cannot see the extra degree of freedom or entropy from the Schwarzschild or JT correction.
Well, you can fall, right? You can fall towards the horizon in the dilaton solution. Whether you're far away or whether you're closer, but if you're closer, you have a simpler description for what's going on in terms of the Schwarzschild. So,
Thank you.
More questions?
I'll ask another general question. Generally, the replica trick, as the name suggests, is a trick. Doesn't always work. There can be cases where the any entropies are not analytic in N, and therefore the extension, there's no unique extension. So how do you account for this in this discussion? Because again, it used the replica trick
yeah.
in an essential way.
Yeah. Yeah, that's why that's why I think there is something that we don't understand yet, which is how do we understand the RT formula in Lorentzian signature? But I think one way it will probably involve this kind of thinking about the entropy as a limit of a more general entropy.
If I can double down on that. So,
Yeah, sorry.
so it's a Riemann surface of high genus, right? And it has many homology, cycles. Yeah. Like we have, so we know which representative and homology to pick.
Well, in general, you want the solution with least action.
It's well-defined problem, like to minimize the.
Well, actually, it's interesting because in certain cases, you have multiple saddles, and you have to pick the dominant saddle. And sometimes the dominant saddle has very interesting properties.
That sounds like a problem for surgeons, kind of.
Yeah.
Okay, more questions? Okay, if not, then let's thank Josephine again.